Okay, so let us continue our discussion on Fermi-Dirac statistics. So from the last video onwards, we have been talking about or trying to learn Fermi-Dirac statistics. So we have learned about the distribution law, right? And then also the Fermi energy. Then now in this lecture, we will try to learn the degeneracy in the Fermi gas. Then from there, what we have done for the Bose-Einstein gas, similar to that, we will try to talk about the thermodynamic functions of strongly degenerate Fermi gas, right? Then eventually we'll talk about electron gas in metals. As I always have been saying for this distributions law or for the quantum statistics, again this lecture is going to involve various mathematical terms, mathematical relations. So I hope you are slowly getting accustomed to these integrations, the integrals in the binomial expansion, infinite series, all those things which are required for this. Okay, so let's try to start the Fermi gas degeneracy in Fermi gas, and I hope you all know what is degeneracy by now. Okay, so there's a deviation of the gas from the ideal gas. Okay, so as you all know that Fermi-Dirac distribution law is given by this particular formula, where your n gives you the number of fermions, right? So fermions are half integral spin particles, right? Or in other words, if I have to say, it carries spin angular momentum who has got odd multiples of h cross by 2. Okay, so now we have been talking about degeneracy in this d parameter, which is e to the power alpha. So if you substitute for d equal to e to the power alpha in this above expression, then you will get like this. Okay, so the another thing which I very meaning shortly I have talked about, that this alpha, which has got a restriction in while discussing for Bose-Einstein statistics, where alpha cannot take negative values, but unlike in this Bose-Einstein gas, alpha can be like it can take positive as well as negative values for Fermi gas or fermions in a cluster of fermions. Why? Just quickly have a look at that. Okay, so in Bose-Einstein statistics or distribution law, if I have to talk about, okay, distribution law, this Ni was equal to Gi by e to the power alpha plus beta e, this minus 1. Okay, so the point here is, now if let's say your alpha becomes sufficiently negative, what will happen? This entire term in the exponent, e to the power that exponent, there's a chance that there's a possibility that that can become negative, right? Because if your alpha becomes sufficiently negative, entire exponent alpha plus beta ei, that entire thing can become negative. There is a possibility. So then e to the power some negative of some number, right? If that happens, then 1 by e to the power of that number, meaning 1 by e to the power of whatever your number is, right? Because you have got what? This entire thing is a negative thing. So that's a 1 by e to the power of that number. So eventually what will happen? This term will be less than 1, but you have here minus 1. So that means what? The denominator, there is a chance that it can become negative. But your n cannot be a negative because these are numbers. How can it be a negative? So that's why there was a restriction that alpha cannot be negative. But unlike these things, now here in Fermi-Dirac distribution law, because there is a plus 1, so there is no restriction on alpha. In fact, you will see that if alpha is positive, around the cases will arise very strong degeneracy or weak degeneracy. Okay, so let's proceed. Now we know that the density of states given by this expression for the energy range E and E plus dE. Again, I am saying script E. I'll be calling it E and so forth. Okay. So the number of particles lying in the energy range E and E plus dE is given by this. Simply you have to substitute for G of E in this. So all these discrete values of Gi or Ei, you substitute the continuous values. Okay. So we have got this earlier. In the earlier lecture as well. Okay, so having got all these expressions, now what do you do usually to study the degeneracy part? Meaning we calculate the expression for total number of particles, here total number of fermions, then total energy of the system. Then let's see what we are. Okay, so substituting for x equal to E by kT, which we have done. This is up to some extent you will see all the steps are similar to what you have done for Bose-Einstein statistics, okay, while trying to learn about degeneracy in Bose-Einstein statistics. Okay, so now, so x you substitute by the x, so you have to just follow, this is basic maths, okay. So so then you just keep on following the way that we have been doing. So your substitute for the in this entire expression, you have to make substitution for x. Okay, so e to the power half will be substituted by, now since e is like e will be x into kt, so same thing will come up here, right? The 1 kt will come from here as well, so that's why it's k to the power 3 by 2. All those things you can carry out by yourself. Okay, now reshuffling, rearranging the terms. I need this term because I know that represents expression for partition function, a translational partition function. Okay, so that's what we have got. Okay, so this is, I hope you are getting the point that this is repetition of what we have done for Bose-Einstein statistics. Now, so the total number of particles, simply we have to integrate over the energy range and entire energy range, right? So the number of particles in each energy level that you have, you integrate out, so you will get this expression, and the total energy of the system will be given by this same, right? You have to just integrate over entire energy range. So by now I think, having got this to integration, if you remember from the earlier videos, you will know that, okay, so this we have solved it out, this integration, right, for in the earlier lecture. Okay, so we will directly use results from that. Okay, now the point is here, this alpha, as I said, it can be positive as well as negative. If your alpha is positive, since d equal to e to the power alpha, so that will be greater than 1, and that will be the case of weak degeneracy. This in fact we have talked about when we are trying to learn, or when I was trying to describe or discuss about the prerequisite for quantum statistics. You can go back to that lecture and watch. Okay, so that's why I have made an effort to describe about this degeneracy parameter even before we have talked about quantum statistics. Yes, so when your alpha is negative, this d is less than 1, that will be case of strong degeneracy. Okay, so in many places you will see I will talk about either d or 1 by d. Okay, so in case of weak degeneracy, 1 by d will be less than 1, whereas in strong degeneracy, 1 by d will be greater than 1. Okay, in fact we will try to calculate numerically a rough value for the Fermi gas, okay, where you will see whether the degeneracy is very high or not. Okay, so let's talk about the first case where alpha is positive. This is again similar to what we have discussed in Bose-Einstein gas, only except that +1 it is becoming a -1. Okay, so I hope you're getting a point where this is +1 and -1. I'm talking about this. Okay, all right, so basically here what you need to do, either to study the degeneracy part, you need to carry out this integration. Okay, just let us rewind ourselves with this integration. So then what you have to do here, you have to take this d e to the power x common, and then okay, so I think I can, in the denominator what will happen, e to the power x, take common 1 plus, so your e to the power x minus like this. Okay, so this entire term comes in denominator, so then if you take only this term to top, then it becomes like this, right, -1. Okay, so then what you have to do, since your d is so 1 by, since it is d is greater than 1, 1 by d will be less than 1, so you can use binomial expansion to carry out this. So if you expand this binomial, if you use binomial expansion, so this expression within the bracket, okay, you will get this. So then now you follow the usual, meaning our mathematical steps. Okay, so you will get this, and then we know this, the standard integral value, right? We have used this earlier, e to the power x, e to the power nx dx. This is given by this will be root pi by 2 n to the power 3 by 2. Okay, so I think it is correct what I am reading. Please check out what I have written for the earlier lecture. Okay, so yeah, so using that standard integral formula that we had discussed earlier, you will end up getting this expression. Okay, so this is your expression for particle, the total number of particles or total number of fermions in the system is given by this. Okay, so again, yes, so from here, from this, because I will be using one expression, so let me, so from here what I can do, I can get an expression for GS, right? So what I can do here, so let me, okay, so when I require I will get that. Okay, all right. So similarly for the other integration, x to the power 3 by 2, and going by the similar, following the similar steps, you will end up this integration, right? So each integration you have to carry out, and we know the standard formula for that. So e to the power 3 by 2 dx, sorry, I have to write e to the power minus nx as well dx, that is given by 3 root pi by 4 n to the power 5 by 2. Okay, so substituting these values of this standard integration, so you will end up getting this expression. What you have to do, substitute these values of the integration, this one, in the expression of, so in this E, total energy, so I will get this, sorry, yes, so I will get this, okay. All right, now I can substitute for the expression of this GS Z by D, so from the earlier equation, so that's what I was trying to derive here. So GS Z by D will be given by N, then whatever there is this entire bracket, what I have to do, I put a simple minus 1 on top, right? Okay, so I hope, so this entire thing comes here in the bracket. Okay, so substituting this in this, so value of this we have got, so this is N into that infinite series expression to the power minus 1. So the N has come here, right, 3 by 2, so let me clean it up, it will be clear. So the 3 by 2 as it is, so KT is there, so N has come from this substitution and then this expression. Next part, I think you all know by now, you need to carry out the binomial expansion of this, then your term wise you multiply. Okay, this we have done, okay, in earlier lecture, so I will just use that result here, right? So I will get this, and then substituting for 1 by D, keeping only the up to the first term, right? So from here I can write 1 by D, so if I keep up to the first term, right, 1 by D will be equal to N by Z, meaning here, like from here I will get 1 by D is equal to N by GSZ, right? Okay, so if I substitute for that, so I will get this expression. All right, so this is your expression for the total energy of a system containing fermions, or a system of fermions, right? Where you can see, as you have, see 1 by D is that degeneracy factor. If you have more and more contribution from that, your gas will deviate. So the expression of total energy, as it says from this expression, your and the expression of total energy will deviate from the ideal gas, as you can see from here. Once you get the total energy, then I can calculate the pressure using this expression which we have been using for calculating pressure. Okay, so what you have to do, simply substitute for the expression of E from this, whatever you have obtained here, substitute that. 3 by 2 is there, 2 by 3, it will get cancelled out, and you will end up getting this. So again, this is the expression of pressure. As you have more and more contribution from the higher order terms, you will get a deviation of the pressure from the ideal gas. All right, so this is, I think, this is quite similar to what we have obtained for Bose-Einstein gas, or Bose-Einstein, yes, so for Bose-Einstein gas, whatever we have obtained. Okay, now in case of strong degeneracy, where your alpha is negative, that means the parameter D will be less than 1, so then your 1 by D is given by this, right? So from this, so 1 by D will be the greater than 1 now, right? So in case of this D less than 1, okay, so the gas will be strongly degenerate at low temperature. So let's look at this thing. Okay, so if your 1 by D is greater, your degeneracy is greater. Means how it will be greater? If your value of T is small, then this entire expression or the entire term will be greater. Or in other case, high density N by V is there, right? So this is N, this is V. So if so for low temperature, high density of fermions, you will get higher degeneracy. That's the learning point from here. Okay, so now since we have seen this, so we have discussed about like Fermi energy, right, or the fermions in case. So then what will happen? We will try to discuss this strong degeneracy part at absolute zero. That means at temperature T equal to 0, and for the case above the absolute 0. Okay, so at in fact, I will try here. We'll mostly discuss at absolute temperature, but at the other part we will try to only talk about the expressions that we obtain. Okay, so we'll see what I'm trying to do. Okay, so the at temperature T equal to 0, that is an absolute 0 temperature. So we have defined these Fermi distribution functions from our earlier lecture. We know that. So that takes a value equal to, this is Fermi distribution function. It's equal to 1 when your energy of the system is, your energy is less than Fermi energy. Whereas it will take 0, okay, when you have the energy greater than Fermi energy. This distribution function also, you know, that it talks about probability of occupancy, meaning, so all the energy states are filled up to the Fermi level, and beyond that all the states are empty. So that's what happens for fermions at absolute 0. That's what is this. Okay, so the number of fermions in the energy range En, so the En E plus dE I can write. So this is what, same the expression where we had where I had, yes. So this is your expression. Here only this meaning this part, right? Because d alpha, if you remember, e to the power alpha was in terms of Fermi energy, we had written minus EF, right, by kT altogether. I hope you can go back and look back to the previous lecture and get back what expression I'm talking about. So this distribution function is given by 1 by of this, 1 by this. So that takes value 1. Okay, if your energy is less than Fermi energy, right? So, and then this expression will remain. So the remaining distribution function part will be 1. And this, so there will be no particle above this Fermi energy. Okay. So if you have that, so I can calculate the total energy of the Fermi gas at absolute 0, which is called a 0 point energy. And you will see that this 0 point energy is not going to be 0, unlike the classical gas or your Bose-Einstein gas. Okay, so so we know that E naught, the total energy of the fermions, is given by this. This also we have derived in the previous lecture. Simply, and then a substitute for the expression of the Fermi energy, that also we had expression derived in the previous lecture. Okay, so substituting that, you will get this. So this is not 0. Okay, now similarly, from the expression of this energy, you can calculate pressure at absolute 0 temperature, again following the same thing, right? So these are usual steps how you calculate. I will remain with this expression. Okay, so for strongly degenerate Fermi gas, energy and pressure has non-zero value even at 0 Kelvin. So this is one important part, which is unique feature of this Fermi gas. Okay, whereas for the Bose-Einstein and classical gas, energy and pressure at absolute 0 temperature is 0. So fermions behave, or they're unique. They're even though it's a quantum gas. I mean, you can think about, like, it follows quantum statistics or consists of quantum particles. Bosons and fermions are not same. Okay, not because of their half integral spin, whereas the bosons are integral spin. But even then, there is a lot of difference in their behavior and their way they exist, right? Okay, all right. So again at absolute 0, this because if you remember, e to the power alpha, meaning you can go back to this expression of d. Okay, so here, so because your temperature, so here see, directly you can substitute that t equal to 0 means what? 1 by d is infinity, right? Or d will be 0. So from there you know that 1 by d is infinity. So if I substitute this, in case of this infinity, I can substitute 1 by d for the case that we are trying to sort it out, or we are discussing, right? So in case infinity, I can just substitute for 1 by d. So in that case, number of particles is given by this expression. Simply I substitute for upper limit with the replace the infinity by 1 by d. Okay, then I will get an expression for 1 by d for the Fermi gas at absolute zero temperature. Okay, so now substituting for this z we already know, right? So I hope the partition function, yeah, so here it is there, right? So z, if you want to write it out explicitly, z is equal to 2 pi m kt by h square. So this is what your, right? So and then one v will come. Okay, this is your z. So this we have used many times. Okay, so if you substitute that, you will get an expression for 1 by d for the Fermi gas at absolute zero temperature. So this is the measure of degeneracy of ideal Fermi gas at t equal to 0. This is what the expression is. Okay, all right, let us continue our discussion, right? For the case where at t greater than 0 but T less than Fermi temperature. Okay, so here this part I will try to give you a separate the PDF for all the mathematical steps involved. So let's not go off the track by discussing the mathematical steps, because it's quite involved, a lot of approximation has to be done. Okay, so only the results let us try to discuss here. So if you follow all the steps how we have done for the earlier cases, so you will end up getting the expression for energy, which is approximately equal to this 3 by 5 n Fermi energy, and in this bracket that you get expression. Okay, similarly from this energy expression you can calculate the pressure that way we have been calculating. Okay, so but we will use the expression for the expression of this energy, okay, for calculating other entropy and specific heat, because we need to talk about temperature just above absolute zero temperature. Okay, so now we'll try to discuss about these thermodynamic functions of a strongly degenerate Fermi gas just above the absolute zero temperature. So we know that from here, so we will use this expression from this energy expression. See, here it is approximated. I have considered up to few terms, right? Or up to, you can see the second term, but here I have put equal, and there's lots other terms are there. Okay, so at such low temperature, the CV is, we know how it is calculated, del E by del T at constant volume. What you need to do, simply see the first term is a independent of t, so anyway that will your differentiation with respect to t will give you 0. Only this term multiplied by this term, then you calculate the usual differentiation. Okay, then you will end up getting this expression, and eventually you will get this. So your CV will look like, so this is your expression for CV, sorry. Okay, so this is your CV in terms of Fermi energy. Okay, for the gas, for the Fermi gas above absolute zero temperature, and if you substitute for expression of Fermi energy, then you will end up getting this. Okay, substitute. So this is your expression, nothing else. You just keep substituting one expression in the other, you will get the term. So basically the most important part here to be noted is that your most of the things are constant. N constant, number of fermions, 2 pi k, all these things are constant except this T. So CV is your proportional to T. So at low temperatures, okay, so here now specific heat at constant volume is proportional to T. Okay, just remember, this is a very important point. Yes, so that's what I was trying to talk about. Now here, from the looking at the expression above, your heat capacity per particle, see, so if you take this n to be this side, so heat capacity per particle would be small for large density. So now n by v, so you can think about this, there is v by n, so it will be 1 by rho, if rho is your number density. Okay, so for smaller okay, so heat capacity per particle would be small for large density. So if you have a very large density of fermions, so then your heat capacity will be small. And also for the small particle of mass m, right? Also because m appears on top, so smaller the mass, smaller the specific heat per particle. Okay, And if these particles are electrons, let's say these fermions are electrons, and this expression will give you the electronic specific heat or the specific heat contribution from the electrons. Okay, and this is, as I said, this is proportional to temperature T, isn't it? So from this expression, as you can see, this is proportional to temperature T. So at ordinary temperature, if you talk about, because you know from the solid state physics that specific heat for an atom is proportional to T to the power Q. So but here, so the contribution from electron is going like proportional to T. So the contribution will be much smaller from the electrons in a metal. Okay, so that's why at ordinary temperature the contribution to the specific heat of the metal due to electrons would be negligible compared to the atoms, isn't it? Because in the atomic specific heat is varying like T to the power cube. Here it is for electronic specific heat varying or goes as linearly, I mean with temperature T cube, and here is T. So the contribution, that's why from the electron side it will be small, or almost it will be negligible, because we know mass is also much smaller. Alright, so this is our learning. Okay, so then once you got the specific heat, we can calculate the entropy, right, by using our usual expression that from here. Okay, so substitute the expression of Cv here, you will get this. So here, see, this part is nearly constant, no T here. So if you integrate out, you will get simply T, isn't it? So your T should compare, here I have writing T square, but see there is one T denominator. Okay, so just to keep the symmetry of this expression, I have written like this. So now you can calculate Helmholtz free energy as well, which is given by E minus Ts. So E is known to you, now T multiplied by Ts is known to you. Do the usual maths. Okay, so the first few terms you can obtain like this. So this is your expression for Helmholtz free energy for the fermions for the temperatures above absolute zero. Yes, so this is your expression. Eventually you will get doing all the algebra. Okay, so then we'll try to talk about this electron gas in a metals. Okay, now this is, you must have had a little bit of idea about electron gas in your solid state physics or meaning other course of solid state as well. Okay, so you can think about a metal something like this. Okay, to analogous to your idea of ideal gas, you can think about metals to be, you know, a collection of, sorry, in a matrix of, let's say, positive nuclei. Okay, so let's say this positive charge I am drawing, this is a nuclei. Okay, so in a matrix of fixed positive charge nuclei, your electrons are, let's say, moving, free particle kind of stuff is, so these electrons are free to move all around like the ideal gas molecules free to move. Okay, so that's why by drawing same analogy, it is called as free electron gas. These electrons are free, they are not bound to the nucleus. Okay, so, and there are many things you can talk about. Okay, so we are not going to deep into the free electron gas model, but I'm just giving a hint of idea of what that is. So basically what you can consider this electron gas. So drawing the analogy of this ideal gas in a box, how these gas molecules are very free to move, they are not subjected to any potential or any force in that. Similar to that, in a fixed matrix of positive nuclei in the metal, let's say, these electrons are, these free electrons I'm talking about, they are free to move around, and then they can collide, they can do all sorts of things that we usually do. Okay, and because these electrons are unlike these classical gas molecules, they carry a spin. And spin is a quantum object. There is no classical analog of spin. And on more and more so, these electrons carry half integral spin, or the odd multiple of h cross by 2 spin angular momentum, isn't it? Okay, and also follows Pauli's exclusion principle. These particles are indistinguishable, they are identical. All these differences are there. Okay, so we can compare just to have a to quick look at how they are different from ideal gas. So they are first of all, they are charged particles, we know that. So the ordinary gas is generally there neutral. Okay, and the concentration of electrons in Fermi gas is large compared to the concentration of molecules in ordinary gas. That is also a true fact. Okay, all right, so let's try to discuss more of this electron gas in metal. Okay, So now for roughly let's try to calculate this degeneracy factor for this electron. Okay, so we know the mass, so everything is taken in CGS unit. Okay, so let's say mass of the electron is this much, gamma spin degeneracy factor is 2. We know that because this is given by 2s plus 1. S is half for the electron, S is spin quantum or spin of the electron, so eventually you will get 2. So if you just take roughly a metal of atomic weight, let's say 100, having density 10, so the volume will be 10 cc, right, 10 centimeter cube. So, and assuming for our simple calculation 1 free electron per atom, so I will get a Avogadro number of, if I have 1 mole of gas, then I will have that many free electrons. So if I plug it in all the values here, okay, m, k is your Boltzmann constant, T I will keep as it is, H is your Planck constant, and 4 pi, all these things you know. V is the volume, which is 10 here, Gs is 2. You will get this expression. Now many things to be learned from here. Okay, now you see this is what 10 to the power 5 by 1.5 T. Okay, see this 1 by D is a absolute large number, 10 to the power 5. Even if you have, so unless you have T comparable to 10 to the power 5, you cannot apply classical statistics to describe electrons, isn't it? Because the degeneration is so high. Is it 1 by D factor is so high, because if your this factor is high, meaning what, your, if this is much less than 1, meaning what, this gas is strongly degenerate, yes, strongly degenerate, isn't it? So I have to apply something different than the classical statistics that we know. So that's why for these electrons, because this degeneration is sufficiently high, so I have to apply Fermi-Dirac statistics for our normal temperatures that it talks. 10 to the power 5 Kelvin, you think about how high is the temperature. In fact, you will see because of this many things will be used, okay, as you are talking about white dwarf and other stuff like that. Okay, so I hope you got the point what I'm trying to say. So here from a rough calculation we got degeneracy is really high in the electron in a electron gas in metal. So that's why we have to apply Fermi-Dirac statistics. Okay. So at low temperatures, electron contribution to specific heat also can be calculated. Okay. So C is given by this, 1 by D is given by this, right? So and we know the Fermi energy expression. So by using these two, okay, so let me show you how I have got this D equal to KT by N. So see, if I take this part is nothing but your Fermi energy by KT, okay, Fermi energy by KT. So D is given by this. So I can write CV in terms of D, right? Okay. So again, using the obtained values of this 1 by D, what we have obtained for our rough calculation is this 10 to the power 5 by 1.5 T, and for our, then let's say your 1 mole of gas, your NK, this is R, which is universal gas constant, in roughly that's equal to 2 calorie per degree per mole in case of CGS, and a pi square let's assume to be 10. And if you put this rough calculation into that, you will get that the specific heat is given by this. And again, you have seen here, we all know that, right? The specific heat is proportional to T. Okay, so you can calculate roughly your specific heat of the electronic specific heat. Okay, so the pressure of the electron gas can also be calculated here, right? Okay, during this usual way. So if you are getting how why 2 by 5 has come. So this is E naught by V, right? So 2 by E naught by V, but E naught is known to us, right? E naught is 3 by 5 NEF by, meaning V is coming from here. So this 3 to 2 by all these things. I hope you can carry out these small maths. Okay. So again, if you substitute for the earlier values that we have used, for a metal of atomic weight 100, density of 10, pressure is in order of 10 to the power 5. So this is again for a very high. Okay, so that's why the for any temperatures, the pressure due to these electrons or the Fermi gas is extremely high, in order of 10 to the power 5. Okay, all right. Now I think I have covered up whatever I wanted to cover up here, right? So this is all about today's lecture. So I hope you all got the point, and we'll see you in one more lecture on Fermi gas, right? Where we'll try to speak the specific heat and white dwarfs, under Shekhar limit, all those stuff. Okay, so for time being, okay, bye bye.